How's it going, everyone? So in this video we're going to be taking a look at some of the foundations for calculus. In essence, it is a preview of calculus. Now, as we mentioned in the first recording, calculus is the mathematics of change. For example, how fast is a ball moving at different parts of its trajectory? Or another example, how quickly is the area covered by an oil spill increasing? So these are all questions that we'll be able to answer using calculus, but we first need to lay the foundations. And I want to start here with the tangent problem. So for starters, what is a tangent line? Well, the tangent line to a curve is a line that touches but doesn't cross the curve. Now in contrast, the secant line is a line that intersects a curve more than once. So here I drew some graph, just some function there, and I drew two lines here. So in green we see a line that's crossing the curve 2 times, so this is the secant line. But in contrast here, the line in blue is the tangent line, and you see here that the tangent line is only touching the curve at this point, so it is only touching it once. Now, how is this related to calculus? Well, remember that calculus is essentially, at least for, well, there's different branches of calculus. The first one that we're going to be seeing is differential calculus, which deals essentially with the study of slopes. Now I want to begin here with an example that is relatable, and it still shows the difference between a secant line and a tangent line. So let's say that you were to take a trip in your car and you notice that after 3 hours you have traveled 180 miles. Well, what would be your average velocity? Now, if you've taken a physics course, you might already know what was the definition for velocity, or how do we find the velocity here. But if not, no worries. This is a calculus course, not a physics course, so let's just kind of review here. How do we find the average velocity? Well, the average velocity, I'll just label it here as V average, is defined here as the changing position over the changing time. So, in this problem here, what is the changing position? So, if you traveled 180 miles, then you moved 180 miles, that was your changing position, over the changing time. So what was the changing time? Well, you drove for 3 hours, so your changing time here is 3 hours. So what is your average velocity? Well, 180 divided by 3 is 60 miles per hour. So you were keeping a good speed here, assuming you were traveling on the freeway. Hopefully not through the streets at this speed. Now, okay, so we found the average velocity, but notice something here. Our formula for the average velocity was a changing position over changing time. So if I gave you a function detailing the position, let's say f of x was, just call it f of t, is the position function, well then the way that we found the average velocity, let's put here v average, it would be equal to, okay, the changing position, so it's going to be the position function evaluated at different times, let's say t1 and t2. So the changing position is going to be the difference between the position at time 2 minus the position at time 1, and that's all over the changing time, so t2 minus t1. Okay, so this is how we get the average velocity. Now this formula might look a little bit familiar, because this is actually just the formula for the slope. And it is the normal formula for a slope that we've seen before. Because again, remember the slope was the change in the y values. So in this case, it's a change in the position functions. Just call this one here y2 minus y1 over the change in the x's, x2 minus x1. So if we picture a graph here, detailing the position, then in the x-axis it's the time, and in the y-axis it is the position given by f of t. So hey, the average velocity is just the slope, and that's the formula that we see here, the average rate of change. Now notice right now I'm not saying the average velocity, I'm just keeping things general. So the average rate of change for any function on the interval from a to b is given by f of b minus f of a all over b minus a, which again, this is essentially what we knew before as the slope. So that's what we see here, that, okay, yeah, the average rate of change, it is the slope of the secant line going through the points a, comma, f of a, and b, comma, f of b. So I'm just going to go back here to my previous graph and say, hey, if I have a secant line, the slope is given by the f of b minus f of a all over b minus a. Okay, well, that's good to know. But since we're on this graph now, what about the slope of the tangent line? So how can I get the slope here? Because if I wanted to get the slope of the secant line, well, I basically had to have 2 points here at, well, located at x equals to a and x equals to b here. But for the tangent line, I only have 1 point. So what can we do? Well, let's discuss it here. Let's take a look at this example where we get to see or compare the average velocity versus the instantaneous velocity. Okay, so suppose that a ball is dropped from a tall building. Now the position given here by s of t is measured in meters after t seconds is given by s of t equals to negative 4.9 t squared. Now what we want to do here is first find the average velocity of the ball during the time interval from 2 to 5 seconds. Okay, so if we picture the scenario here where we have the ball dropping, I'm just going to exaggerate the trajectory here. So if we drop the ball, so notice here it's a quadratic function that's opening down. So it's the parabola here. Let's say, here we go. Again, just exaggerated here. Then let's see, at time equals to 2 seconds, let's say we have it here. Here t equals to 2, and here's t equals to 5. And again, this is the t-axis representing the time, and this is the y-axis here representing, or the position axis given here by s of t. Okay, so what we want to do is find the average velocity, which is, again, remember, the slope of the secant line. There we go, there's our secant line. So what is the slope? Well, the slope, which is the average velocity, is given by the change in position, or the change in the y's, the y-axis here. That's going to be s of time 1, or time 2 minus time 1. So it's going to be s of 5 minus s of 2 all over the changing time, which is 5 seconds minus 2 seconds. Okay, so this is going to give us, let's see, s of 5 is going to be the function evaluated at 5, so it's going to be a negative 4.9 times a 5 squared minus, put here the minus in red, another negative 4.9 times now 2 squared. And this whole thing is going to be all over a 5 minus 2, which is a 3. So let's see, what do we get? Well, I'm just going to go to the calculator here. A negative 102.9. So let's see, negative 102.9. Now, what were our units? Well, the time was measured in seconds and the position in meters. So it's meters per second. Okay. So this is the average velocity. Now notice it is negative. That makes sense because if the object is falling, then if it's coming down, it's getting closer to the ground. It's coming down again due to gravity, so it's coming down with a negative velocity because, again, gravity pulls us down. Okay, so this is the average velocity from 2 to 5 seconds. But now let's see if we can find the velocity after 5 seconds. Now, in other words, hey, what is the velocity at 5 seconds? So we want to find out, hey, exactly at 5 seconds, yeah, what's going on there? Now, this is known as the instantaneous velocity, the velocity at an instant. So how can we do it? Because again, remember, if we wanted to find out the average velocity, well, we needed 2 times. So if we only have 1 time here, precisely at 5 seconds, what can we do? Well, for now, we can be, I don't know, a little bit clever here and say that, okay, you know what? I really cannot find the instantaneous velocity at exactly 5 seconds, but what we could do here is find out the average velocity in smaller and smaller intervals close to the 5 seconds. And I'm going to do that here in a table. So let's select our intervals that are close to 5 seconds. So I'm thinking we can find the average velocity between 5 and 5.1 seconds. So let's say that our time is between the 5 and the 5.1 seconds, but we can get smaller intervals. What would be the average velocity between 5 and 5.01 seconds? Now for good measure, let's also do the average velocity between 5 and 5.001 seconds. And out of curiosity, let's do another time interval that's close to 5. Let's say between 4.99 and 5 seconds. So what would be those average velocities? Because notice, I mean, if I'm getting smaller and smaller intervals, then I don't know, I think we could make a good guess at what might be the exact velocity at 5 seconds. So let's see. If we figure out, okay, what is the average velocity between 5 and 5.1, we can go to our calculator here. And, well, I'm just going to list out the numbers here, guys. But we just use the calculator to find them. Okay, so these are the values that I got. And it seems like the smaller my time interval became, the closer the average velocity was getting to 49. I want you to be careful with this last example here. It doesn't seem like we're getting closer to 49, but notice that we're choosing a time interval between 4.9 and 5, which is more akin to this time interval. But I encourage you guys to check this on your own. If you try a time interval that's smaller, let's say a 4.9999, put here 4.9999 and 5, you will see that you are indeed getting an average velocity of negative 49. So if I were to take a guess at what might the instantaneous velocity be when time is equals to 5, in other words, the velocity exactly at time equals to 5, then we should be getting a 49 meters per second. So just put here at time equals to 5, the instantaneous velocity is equals to negative 49 meters per second. Okay, now we got our way here by an estimate of what the instantaneous velocity will be, but later on we'll figure out how to get it exactly without the need for multiple approximations. Now to recap here, the average velocity was referring to the slope of the secant line, but the instantaneous velocity, which required only one point, is going to be now known as the slope of the tangent line. Because again, remember, the tangent line was only touching at one point, and if, for example, we're trying to find the instantaneous velocity, then it is the slope at a point, so that is the slope of the tangent line. Okay, now I want to take a look at another example here, getting practice with finding the average rate of change. So let's say that we want to find the average rate of change for the function f of x equals to x squared plus 2 over the following intervals. So first on the interval from 1 to 2, then from 1 to 1.5, then from 1 to 1.1, and then 1 to 1.01. So as you can see, our intervals are getting smaller and smaller. Now, I want to give you guys a shortcut here. Rather than going to your calculator and start plugging in values, I want you to use the formula. So again, remember, the average rate of change was essentially the slope. Now, let me write down the formula. Okay, so here's the formula, and we basically have the function here, and our intervals are given here. First the a, then the b. So rather than putting everything in our calculator, let's simplify this formula with the given function. So if our function here was x squared plus 2, then evaluating the function at b and a is going to give us here ab squared plus 2 minus an a squared plus 2. Well, technically that's not correct because we are missing one crucial detail. Right now, this was the function evaluated at b, but we're also subtracting the function evaluated at a. Now, if you remember our review on functions, I mentioned that whenever you're subtracting a function, if the function has more than one term, we got to make sure that we include parentheses here. So we include the parentheses now. Okay, so let's simplify this a little bit more algebraically, and then we can start plugging in the numbers. So if we simplify it, let's see, we're going to have ab squared plus 2. Now we distribute the negative minus an a squared, distribute the negative here to the 2, so minus 2, all over b minus a. Now notice I have a 2 minus 2, so that cancels. So this leaves us with ab squared minus a squared all over b minus a. Now can we simplify this a little bit more? Well, you might be recognizing that on the top we have a difference of squares. So if we factor it out, and that's going to be a b plus a minus, times a b minus a all over a b minus a. Now what do you know? I can simplify it a little bit more here. So it looks like the average rate of change is actually given by b plus a. Okay, well that's good to know. So if we take a look at our first example, if we want to find out the average rate of change between 1 and 2, that's our b, that's our a, then b plus a is going to be 2 plus 1, so that's 3. Now the average rate of change between 1 and 1.5, well then now that's going to be 1.5 plus 1. Okay, so it's a 2.5. The average rate of change between 1 and 1.1, so now we are at a 1.1 plus 1. So notice here the only one that is changing is the b. The a is always staying at 1. So we're going to have here a 2.1. And lastly, we're going to have a 1.01 plus 1. And that's equals to 2.01. Now, you could have avoided using the algebra here, but personally I think it's a little bit more tedious if you go to your calculator and do this for all the different intervals, because once we perform the algebra, which is again an excellent exercise in polishing our algebra skills, then the end result is something much more simpler. Now, if I were to ask you guys, hey, what do you think the instantaneous rate of change at 1 will be? Well, you're seeing here that our time intervals are getting really small, and you're getting values that are closer and closer to 2. So I would say that a good guess to get the instantaneous rate of change here, or a good guess of what's the instantaneous rate of change at 1 is 2. Now, I want to illustrate what we're doing here graphically. Alright, so in the last exercise, we found the slope of the secant line using intervals to the right of x equals to 1. Now let's see what's happening on intervals to the left of x equals to 1 and see graphically what is going on. So on the first interval from 0 to 1, I got an average rate of change of 1, and I labeled the graph here in blue. Now on the second interval from 0.5 to 1, got an average rate of change of 1.5, and I labeled the graph here in green. Now on the interval from 0.9 to 1, got an average rate of change of 1.9, and I labeled the secant line here with orange. And on the last interval from 0.99 to 1, I got an average rate of 1.99, and I label here the graph in red. Now, notice that it didn't matter whether or not we were using intervals to the left or to the right of 1, because ultimately kind of looks like the average rate of change was indeed getting closer and closer to 2. Okay, so graphically what is happening? Well, we get to see here that on the largest interval from 0 to 1, labeled here in blue, I have the secant line represented here. But now, as the intervals were getting smaller and smaller, the smallest intervals being in orange and in red, well, it kind of seems like the secant lines were approaching the tangent line at x equals to 1. And that is going to play a very, very crucial role when we get to our study of slopes. Now, it is very important, guys, that you do recognize the difference between the average rate of change and the instantaneous rate of change. The average rate of change is an estimate and requires 2 points, while the instantaneous rate of change is exact and requires only 1 point. Okay, so this is it for this particular section. It was rather short, but we're going to be coming back to these ideas in the next couple of sections. Alrighty, so this is it for today. I'll see you guys later.